Hi, my name is Anston and I am the Systems and Applications Engineer for the Simple Switcher Group at Texas Instruments. Today I'm going to show you inverting made simple using the LM4 family of parts. This family has a very high light load efficiency, 27 microamps of operating quiescent current, current mode control and internal compensation. Furthermore, this family of parts can go all the way up to 60 volts in a fully synchronous design, which means you can see efficiencies of up to 95%. Now let's take a look at some places that we would require an inverting rail. The biasing stage of op-amps frequently require a negative rail to power them up. In the communications platform, we require negative rails as the switching circuit input for fiber optics. We also need them as telecom power amplifier rails. I have a schematic here that's based on the LM4600x that can showcase how an inverting can be made simple. If you notice, the ground terminals of the IC are all referenced to the negative rail. You will also notice that we have only one bypass cap connected from the input to the output. By placing this bypass cap, we eliminate the need for more caps on the input and the output reference to system ground. Another important thing to note is the IC ground is different from the system ground. I mentioned earlier that the IC ground is at minus 12 volts, whereas the system ground is at 0 volts. The resistor that we've used here to enable the part is pulled up to Vn. However, if this application needs to be used to start up into a load, then it's advisable to use an enable supervisor. Let's take a look at a design example that makes use of a typical telecom application. The LM4600x datasheet says the maximum operating voltage is 60 volts. The maximum average inductor current is 2 amps. Using this equation, we can subtract the output voltage from the maximum operating voltage and get 48 volts. 48 volts is also a very popular bus operating rail in telecom applications. For this design, we know we're going to use 48 volts as our input and we want a negative 12 as our output. The duty cycle can be calculated using this equation to get to 23.8%. Finally, the maximum operating current that this part can supply is dictated by this equation, which is the average inductor current multiplied by 1 minus the duty cycle. That comes out to be 1.5 amps. Now that I've shown you the design example, let's take a look at a real EVM that we can practically showcase this experiment. We've got a scope here that shows us the input and the output voltage rails. To my right, we've got meters that show us the input voltage, the output voltage, and the output current. Farthest to my right, I have a load and I have a power supply that can go up to 50 volts. In front of me, we've got the EVM, which has the LM4600x powering it. I'm going to now switch on the power supply and we're going to see a startup waveform appear on the scope. The input voltage set to 48 volts and the current set to 4 amps. I'm now going to turn on the power supply and deliver 48 volts to the board. As you can see, the output rail has dropped down to minus 12 volts and the input rail, when the input rail has climbed to 48 volts. This is a smooth, soft startup. Let's take a look at our meter readings. As you can see, the input voltage meter reads 48 volts. The output voltage meter reads minus 12. And down below, the output current and the input current meters show that there is no load present. Our design examples specified that 1.5 amps was the maximum load current that we could achieve. So let's try that out. I'm going to increase the load to 1.5 amps, and you're going to see that climb out up here on the output current. There we go. We have successfully reached 1.5 amps on the output, and we are still regulating very cleanly at -12 V out. In summary, the LM4360x and the LM4600x family of parts make inverting very simple. For more information, please check out simpleswitcher.com. Thank you for watching.